we're going to find the general solution to this differential equation. And now I have the title in here, exact differential equations, but I want us to practice deciding what method we're going to use to solve a differential equation, in case we ever encounter one outside of the context of a certain topic. So let's look at our flow chart over here. It might be a little bit hard to see, but hopefully you can still read it. I'll make it a little bit larger for the sake of the beginning of this video. All right, so we want to first ask ourselves, what's the order of our differential equation? Is it a first order equation? In this case, yes, the derivatives that appear only have a first derivative. So the highest derivative is a first derivative. I'm going to go ahead and follow that branch down. So yes, it's a first order equation. If it were a higher order equation, we're going to learn some techniques to deal with those later. But we do have a first order equation. Then we want to ask ourselves, is the equation linear? Well, in this case, we have this y squared here. That is preventing the differential equation from being linear. This is a nonlinear equation, so I'll go ahead and follow that branch down. Then we ask, is the differential equation separable? You could try separating out the variables here, but you would find that it is not a separable differential equation. So we will go down this branch and ask ourselves, is this differential equation exact? And that's the topic for this video. So let me get this out of the way. Okay. So we've decided we're going to check whether or not this function is exact. And if it is, we'll apply our techniques for solving exact equations. All right, so one, we should identify, or we should determine what are the functions m of xy and n of xy in the form of the exact differential equations we've talked about. In other words, we want to put the equation in the form m of xy plus n of xy times y prime equals 0. At this point in time, this differential equation is not written in that form. So we're going to need to move things around in order to get it in this type of form. What you'd want to do then is group all the terms that have dy dx, which is that y prime, and then group all the other terms together. So all the things that don't involve y prime are 6x squared minus y plus 3. All the terms that do involve y prime or dy dx are 3y squared minus x. And then I would also need to subtract this 2 to the other side. So minus 2, and I can factor out that dy dx. So now this is in the appropriate form for us to determine that this first expression is capital M, and this second expression is capital N. So in this case, M is here, N is here. Now, if our differential equation is exact, then M would be equal to the partial of psi with respect to x, and N would be equal to the partial of psi with respect to y. So just keep in mind, if the equation is exact, that's kind of the situation we're in. So let's check. Let's go to our second step here. Oops, slightly different color. Here we go. Let's check. And to check if the differential equation is exact, we need to check whether, check if the partial of m with respect to y is equal to the partial of n with respect to x. So let's go ahead and do that. The partial with respect to y of capital M is the partial of 6x squared minus y plus 3. That gives us negative 1, because the 6x squared we treat as a constant. So the partial with respect to y of that is 0. Partial with respect to y of 3 is 0. And the partial with respect to negative y, partial of negative y is negative 1. All right. Next, we want to compute n sub x. So we take the partial with respect to x of 3y squared minus x minus 2. Similar story, we also get negative 1 here. So because these two quantities are equal, we know that the differential equation is exact. So this ODE is exact. That means that we can find such a function psi whose partial with respect to x is 6x squared minus y plus 3, and whose partial with respect to y is 3y squared minus x minus 2. So let's do that. the way that I do that typically is I compute the integrals of m and n, and I just compare them to figure out what psi should be. So we're going to compute that psi should be equal to the integral of m with respect to x, and the same psi should be equal to the integral of n with respect to y. So we're going to compare those two things. So we compute the integral of 6x squared minus y plus 3 over over x. Okay, so we're computing this step here. And we'll get 2x cubed minus xy plus 3x plus some function of only y. So remember, we're integrating over x, but if we take the partial of this expression with respect to x, we would totally get rid of any terms that are only involving y, because we'd be treating them as a constant. So we have to take into account that those might have disappeared in taking a partial. So that's that some function of y. Let's also do the same idea, integrate now n, which is 3y squared minus x minus 2, this time over y. So we'll get y cubed minus xy minus 2y, this time plus some function of x, because we integrated over y. And if we took a partial of this with respect to y, we would have gotten rid of anything that only involved x alone. All right, we're going to go ahead and then compare. So compare the expressions for psi. Again, because both of these expressions should be equal to the same functions, we need to figure out kind of how to piece things together. All right, let's look at the things that involve x's in the first, only x in the first term. In this first line, the things that involve only x's are 2x cubed and 3x. Those are going to correspond to our g of x, our function that only involves x's. In our other expression, the functions that only involve y are going to give us f of y. That would be, sorry about that, that would be y cubed and negative 2y. Notice that the things that involve both x and y are the same in each equation. So that should happen if you do this correctly. Anything that involves both x and y should match each other in both expressions for psi. So now we just kind of piece these things together. I know that psi of x comma y is going to be 2x cubed minus x times y plus 3x plus y cubed minus 2y. I don't need to include both terms of x, y, because they're both kind of accounted for already. So I've got 2x cubed minus x, y plus 3x plus y cubed minus 2y. All right. And lastly, we need to write down our general solution. So now that we've found psi, our general solution is just psi of x set equal to some arbitrary constant. So finally, our general solution is 2x cubed minus xy plus 3x plus y cubed minus 2y equals some arbitrary constant. And that's our final answer for our general solution to the differential equation. That's it for this example. Let me know if you have any questions.